this concept to everybody, and then I want to ideally get from you guys critiques of this and suggestions on concrete, cheap experiments that can be conducted to test all or part of this methodology. And the idea here is, can we upload a human brain in less than 5 years? I've thought for a long time this is an insane idea. I no longer believe this, and the core of this is the transformer models change everything. And not taking that into account is very silly. And so how do we approach this? All right, so the core of this idea is that we think from neuroscience evidence and from clinical evidence, most especially deep hypothermic circulatory arrest, that the brain contains a structural language that describes essentially everything that's necessary to define what a person is. And in this case, I will say the structural language is probably around 10 or less discrete proteins, and the entire nanoanatomy of the brain at a sufficient level to trace every synapse back to every neuron. All right? I think you can defend that. If that's the case, the current expansion microscopy combined with the current state-of-the-art light sheet microscopy is sufficient to scan an entire brain in less than a year using 1,000 light sheet microscopes at 16 by 16 by 16 nanometer volumetric pixels, and for less than $100 million. So that's kind of what we're playing with. This is achievable. And normally if you had that data set, you would not be able to do anything with it. It's a vast 3D model. What do you do? Even tracing it is hard. But because of the advent of the transformer architecture, I would say that what we generally have here is an algorithm that solves language in full generality. If there is data that has some sort of grammar to it, some sort of structure, these algorithms empirically simply can pick that out and understand it and master it and then generate plausible extensions to it. So I think ultimately the structural language of a brain is scrutable by these types of networks and probably simpler in many respects than English. I don't actually expect the structural language of a brain to be in any way encrypted, for example. The brain's got to be legible to itself, so this stuff in some way has to be straightforward. So what I think you can do is if you train a transformer model to be able to understand the structural language to the point where if you masked part of a connectome, it could regenerate it, trace over it, to where if you set it to the task of hallucinating an entire mouse brain, right, it will generate the appropriate high-level structures, and when you look at low-level structures, those will be sensible. That if it generated these structures, it would not have things that have epileptic seizures, for example. That in some way this transform model, if it has sufficiently low perplexity, could even distinguish between two things that look reasonably correct in terms of the overall grammar of the system, but one's a valid memory engram and one's kind of nonsense. I think you can eventually distinguish these the same way that the large language models can distinguish between two paragraphs, one of which tells a coherent story, one of which has plot holes in it. If you're able to do that, then a model like that essentially already is an upload. It's got 99.9% of the stuff that you need to describe the dynamics of the brain, because the dynamics of the brain, the complete dynamics, are latent in that structure, the same way that a brain that's been cooled down and has no dynamics anymore, all of the potential dynamics are latent in that cold, static brain structure. So I see going from form to function, if you really understand the grammar of form, as being a fairly straightforward process, something that's more akin to just sort of waking it up rather than really having to learn a huge amount of stuff. To make that more precise, I expect that a large amount of transfer learning will be possible if after having gotten a transformer that can understand structural language, you set it to the task of predicting essentially any live data of sufficient resolution. I think fMRI in this case is potentially sufficient, because the only way to effectively predict the next frame is to actually pay attention to the distilled engram logic of the structure in a way that predicts the frame. So that's the core of the idea. I would say the overall technical feasibility of each layer of this, as I'm estimating it, is doable with the current transformer technology, the current expansion microscopy, the current light sheet microscopy, but like sort of barely. It's a very complex tech pipeline, but it's something that's comparable to other scientific projects that have been done. And the main thing I'm interested in is critiques of this and lesser experiments that can be done to help test it out. So one thing that I think is a sensible thing is you would certainly want to do this on a mouse beforehand. You'd want to do it on simpler creatures beforehand. But even uploading something like ChatGPT-2, I think, is a reasonable task where you would pretty print the network of GPT-2 so that it's a 3D model of a network. And then you would simulate microscopy on this, and then you would try to read out the logic of its connections and build a controller model, et cetera. So that's the core. What do we have to talk about? Yes. And my question is, like, in general, I think the right test for whether you have an upload is, can it detect hidden state? So I have an 80-bit password that opens up my laptop, right? If there's some set of interrogative things that you can get out of my brain that doesn't include that as part of the training data, but nevertheless, you can get that 80-bit password, then yeah, I buy that, because I'm using that as a surrogate for other important hidden memories, like early childhood, formative memories, etc. I would believe, for example, that if you said, hey, this personality quiz, if you answer these questions, that defines everything that you have. Like, I say no, okay? But you know what? If I answer questions, you derive my laptop password, fine. Like, that works. I'll believe it. So I think that's the right thing to be thinking of. And you can do password equivalent experiments for mice for other things. So,
I'll
yeah,
ask in a second to break it down for me to one line question, but for now we can take questions.
Password experiments.
I will write it down. Don't worry about it.
Design me a password extraction experiment. That is my
Alright,
question.
we'll do
How
it.
many times do we get
Lots
to
of
guess the
questions.
password?
You need to be able to do it once.
Once, okay.
Yes.
So 3 times.
Like, it has to be fair. Yes, Rita.
For this language you're trying to learn, the voxels are they the characters? Is something else the characters?
So there's a question of what the equivalent of tokenization is for a brain data. I call it feature extraction. And that will make or break this, because you're dealing with 350 exabytes of raw pixels, which you literally cannot store that. It has to be streamed and processed on the scopes into some sort of form that's sensible. And I can think of a bunch of different ways. I think on the order of 160 bits per cubic micron is sensible to still maintain connectomic traceability. I think traceability is a core requirement of whatever features you're extracting. But a wise choice of this makes or breaks it. And ideally, the entire chain of this is fully differentiable so that you can take the attempts to do fMRI predictions and learn the correct feature extraction from that.
And you don't have to start with the human brain, of course. You can start with
That's correct.
smaller.
Yes.
Yeah.
Same thing with the proteins, right? Like, you start with no proteins labeled. You consider the perplexity of the network in generating masked parts of the network with and without the protein label, right? Some proteins won't help you, and so those don't matter. Some proteins help you reduce the perplexity of the network, and those are carrying useful grammatical information about what the stuff means. So you can do that.
Give 1 more minute.
What else we got?
I'm kind of wondering about step 4 here, in particular, sort of how you think about plasticity. You sort of explained how you think forms of transfer learning from fMRI could perhaps help account for this, but it seems like there's such intensely fine-grained dynamic processes going on, such as with glia and other that are an extremely fine scale that fMRI definitely doesn't cover. How do you think you can account for such plasticity processes?
So it'll have the full descriptions even of the glia, right, from that original data.
But only static ones, right?
That's right, static. And then the question is, do you attend to it? I think that's a big question, and I do think that we will eventually develop what they call an infinite context window types of transformers. And so then you could attend to both the structural data and all of the previous simulated fMRI frames. But then that would give you like this weird sharp distinction in how the memories work, where the memories pre-upload are of a different nature than the memories post-upload. And maybe that's good enough for like the first iteration of this.
Awesome. Thank you so much.